So in the previous section, we have developed the delta L vector, the displacement vector, which corresponds to externally applied forces in a release structure. And now the next step in this analysis of flexibility matrix method is to develop the flexibility matrix. This matrix. Flexibility matrix, which is the multiplier of the R vector, will contain delta 11, delta 12, delta 21 and delta 22. These are the elements of this matrix. If you write this as an equation in longhand form, this equation, we will have delta R1, the first element of this vector, equal to delta 11 R1 plus delta 12 R. So delta 11 is a coefficient of R1, delta 12 is a coefficient of R. Similarly, delta R2, second component of this vector, will be equal to delta 21 R1 plus delta 22 R. Now, to develop the coefficients delta 11, delta 12, etc., say to develop the first one, delta 11, we can put R2 to 0 so that this term will vanish from picture, and set the value of R1 equal to 1 so that delta R1 is equal to delta 11 simply. And to find the value of delta 21, again R2 should be 0 and R1 is equal to 1 so that delta R2 will be equal to delta 21. To find out delta 12 and delta 22, we can set the values of R1 to 0 and R2 to 1 so that delta R1 then will be equal to delta 12 and delta R2 will be equal to delta 22. And let us recollect, delta R1 and delta R2 are the displacements corresponding to coordinates 1 and 2 due to the application of the forces R1 and R2. Fine. Now we are going to develop this matrix coefficients one by one. So to develop the first column of this matrix, we are going to put R1 is equal to 1 and R2 is equal to 0. That is given in this picture. Here I have put this moment at this, say, support equal to 1 and the moment here equal to 0. Now the rotation of this span at this end will be delta 11, that is rotation corresponding to coordinate 1 due to a moment applied corresponding to coordinate 1 will be delta 11. The rotation corresponding to coordinate 2, this coordinate, due to a moment applied corresponding to coordinate 1 will be delta 21. Now if you find out delta 11 using the results developed in the previous section, that is when there is a simple support span subjected to a moment at one end, the rotation at the same end will be given by m into L divided by 3 EI. M is the applied moment, L is the span, EI are the Young's modulus and second moment of area respectively. Now theta 2, the rotation at the other end, the far end, will be equal to ML divided by 6 EI, which is half of this rotation. So delta 11, if you replace m by 1, L by 3 in this equation, it is 3 divided by 3 EI, and as per sign convention, a clockwise rotation here is assumed as positive as per the coordinate over here. So delta 11 will be positive. Now delta 21 as per this equation would be m is equal to 1, L is equal to 3 divided by 6 EI. Now the sign, minus sign, is because the coordinate is assumed as clockwise, whereas the rotation here is anti-clockwise. That is why we have a minus sign. So delta 21 is equal to minus 1 divided by 2 EI. Now further, to develop the second column of this matrix, we are going to set the value of R1 to 0 and R2 to 1. So when we apply moment equal to unity corresponding to the second coordinate, we have this picture. One is applied here, one is applied there for equilibrium. Now the similarly supported spans, these two spans bend in this fashion, and now the rotation here will be anti-clockwise, and this will be our delta 1, 2. Rotation or deflection corresponding to coordinate 1 when we apply a unit rotation corresponding to coordinate 2. Delta 2, 2 will be sum of these two angles, this angle and this angle. That is delta 2, 2. Now, delta 1, 2 is given here. That is equal to, using the same relation, second one to be precise, it is equal to m is equal to 1, L is equal to 3, and divided by 6EI. Now this is anti-clockwise, but the coordinate here is clockwise, so we should have a minus sign for that. Minus 3 by 6EI, this is minus 1 by 2EI. And further, delta 2, 2 will be equal to, this angle is clockwise, as per this coordinate clockwise is positive, and this rotation will be as per this equation 3 divided by 3EI. M is equal to 1, L is equal to 3. That plus this angle, which is due to a moment here, and the rotation is anti-clockwise. Again, we have to make use of the same relation. So M is equal to 1, L is equal to 4 there, divided by 3. So we have 7 divided by 3EI. As per the convention, a clockwise rotation here is positive and anti-clockwise rotation here is also positive. So delta 2 is equal to 7 by 3EI positive. So the matrix, delta matrix, will be equal to, keeping 1 by EI outside, one, delta 1, 2 is minus 1 by 2, delta 2, 1 is minus 1 by 2, delta 2, 2 is 7 by 3. That is the delta matrix. So we have everything in place. Delta vector containing 0 and 0, delta L vector containing 1 by EI into 4.5 and minus 14.5, and finally this delta matrix 1 by EI, 1, minus 1 by 2, minus 1 by 2 here, 7 by 3. We can observe that this matrix is a symmetric matrix. Now, solution of this equation will be like, redundant forces R is equal to delta inverse within brackets this delta vector minus delta L vector. If we do that properly, we are going to get R is equal to minus 1.36 and 5.88. Instead of inverting this matrix and finding the product delta inverse into this vector, you can also solve this equation as a solve this particular set of equations as set of two simultaneous equations. That is pretty easy. So the solution procedure is not going to be discussed in detail in this section. Rather, we are interested in the formulation of the flexibility matrix, the formulation of the displacement vector, and the result and its interpretation. Now, to interpret this, let us go back to the original beam over here. minus 1.36 is the moment at this end. MA will be equal to minus 1.36 and MB will be equal to 5.88. If I plot that over here, minus sign represents anti-clockwise moment because this is chosen as clockwise. So this number is 1.36, and as per this coordinate system, clockwise here, anti-clockwise here are positive. So 5.88 is positive. That means this moment is 5.88 and this moment also is 5.88. These are the support moments. And finally, if you draw the bending moment diagram, we have 1.36 is anti-clockwise. We can draw this ordinate towards the tail end of the arrow mark like that. And these ordinates again to the tail end of the arrow mark. So this is 5.88. This is 1.36. We can connect them together. The moment here is 0. Now above this is a support moment diagram. Above this we can superimpose the simply supported bending moment diagram. Now the support moment diagram is going to be hogging in nature, and the simply supported bending moment diagram is going to be sagging in nature. So if you superimpose the simply supported bending moment diagram, the simply supported bending moment diagram for a simply supported span with UDL alone would be having maximum ordinate at the center and variation like a parabola. This ordinate is given by W L square by 8. That is 4 into 3 square divided by 8, which is 4.5, of course. Now the bending moment diagram, simply supported bending moment diagram here would be an isosceles triangle because this load is at the center, and this ordinate is WL by 4, and that is 10. 10 into L divided by 4 will be 10. Now because the simply supported bending moment diagram and the support bending moment diagram are of opposite nature, the disjoint portions are supposed to be shaded. That is, the common portion is actually cut off, and disjoint portion is the actual bending moment diagram. So the shaded portion is going to be the actual bending moment diagram. We can find the ordinates everywhere in the beam. Bending moment is given in kilonewton meter. So that is the final step in this procedure. So essentially we have solved the compatibility condition to arrive at the bending moments as well as to draw the bending moment diagram. In due course, we have assumed a coordinate system. That is the most important thing over here. That is the structure coordinates. We have released as many number of moments or forces from this as the degree of static interdependency first, and assumed coordinates corresponding to the degree of static interdependency, and then we have developed the delta vector, delta L vector, and this delta matrix, and evaluated the value of capital R, the unknown forces. And then we have found out the other forces or the bending moments and drawn the bending moment diagram. That is essentially the procedure of the flexibility matrix method for a two-span continuous beam.